Okay, so this will be the last video on the ethanol example, and now we've got to talk about yields, instantaneous yields, and also cumulative yields. So I've introduced some even more new emojis in this section, but let's get on and explain the graph that we have obtained in example 6.2. What is yield? Well, if you think about it, yield is just the ratio between the push divided by the pull. So I've got one example here of a good push divided by a good pull, and this is a poor push divided by a good pull. Okay, so yield is always a relative thing. We cannot look at the absolute values of rate here because we divide the push divided by the pull. Now, instead of having this whole big thing as an emoji, I'm just going to use this as an indication of a good yield. Okay, so a good yield is nothing more than a good push for a good pull. So have a look at this figure. Most of the flux, so that'll be the glucose pull, pull, and this will be the ethanol push, and only a small amount of the carbon is getting lost, therefore that small little stream over there, and therefore the green. So this represents a good yield. A poorer yield, or let's call it a bad yield, will be indicated in red, and what we have over here is that the glucose pull ends up with a poor ethanol push. Why is the push poor? Because a lot of it is lost in this fat big arrow over here. So you can see it's thicker than the green over here. So this will be poor yield. And we will typically in this example get the poor yield because the big arrow is a lot of glucose that is going down into growth. So we can quickly have a look at the gauges for this example. So let's put the two gauges here. We've got the mu gauge and we've got the theta gauge. So typically you will find in this example that when you have a good yield, the theta is pushing properly. Okay, so maintenance will typically remain fairly high until there's no more glucose. But you get that at a low value or even a zero value of mu. So we want to shut down the mu factory, not to make biomass, and then most of the flux can end up as ethanol, and you will end up having a good yield, which is this green arrow. Okay, the reverse is true for the ratio where we have a poor yield, because over here we will still have the theta factory power plant running at a more or less maximum capacity or close to maximum capacity, and mu now will also be running at a high value. So a lot of the energy that gets made in the mu factory is spent on making biomass, and that is the reason for this thick red arrow over here, where you have a poor yield because only a small fraction, well, not as big a fraction as over here of ethanol is ending up when compared to the amount of glucose that you have used. So what is YSE? You guys know this by now. It is really just the rate of ethanol formation divided by the rate of glucose depletion. Okay, and this will be wherever you work. It's unlike rates that we did in the previous video. The ratio between the volumetric rates will be the same as the ratio between the biomass-based rates, because this is really just because the volumetric rate is merely the biomass-based rate divided by the multiplied by the catalyst concentration. So you can see there's no distinction. We're not going to have a differentiation between yields and the yields based on the bug and yields based on the fermenter. They are now the same thing. So at the yield graph for the same example, so you can see that there's a clear it starts at a low value, there's a clear increase in yield, and even though it's maybe just 20% or so, typically this can be very important to utilize your product, because it can be major in terms of the economics of the process. Let's just make this one smaller so that we have so this is a supposed to be the same figure as the one we just had. And basically what we see over here is that the poor yield region is over here. Okay, sorry, that's the wrong one. The poor yield is over here, while the good yield is over here. And then you have a gradual transition from poor yield to good yield. What is causing this? Well, as I said before, right at the start of the fermentation, this will be at time 0, both the theta factory and the mu factory were operating at close to full capacity, and this really caused a lot of biomass formation, and therefore the ethanol per glucose is now poorer than what it is in the end. The end is over here, where we have that maintenance production section. Why would this be? Well, because in this section, theta, if you remember correctly, was still operating close to the maximum, while if we take the mu factory over here, it was now operating at 0. There was no growth, and because there was no growth, there was also no glycerol formation under non-growth conditions. That's an interesting result from the flux model. See if you can understand that. But here we have the good flux. Most of the stuff is going to ethanol. There's still some CO2 being made, but this is definitely the target higher yield that you obtain under maintenance conditions. So even though the rate of maintenance was slightly dropping over here, you won't see it in the yield graph because the yield is just the ratio, and the ratio of growth to maintenance were constant in this section because only maintenance were occurring in this specific section. So lastly, go to a cumulative product yield. In the notes we use the fancy word cumulative product yield. What is that? Well, it's really just the integral of the yield. So, and it will give you some sort of, you can say, an average type of yield. In this case, it will be S divided by E. And our calculation will really just be saying the amount of ethanol formed. So that will be the concentration of ethanol right in the end when glucose is consumed, times the volume, because concentration times volume is amount, divided by the glucose, and you've got to say glucose consumed, so it will be CS initially minus CS final. This value will typically be 0 times V. So this will basically, because the CS final value should be 0, you complete all your substrate, you end up with the cumulative value just being the final ethanol concentration divided by the initial glucose concentration. And that value, if you calculate it, should be, if we have a look at the map, we had a minimum yield value and we had a maximum yield value, and the answer, which is a weighted or integrated average rather, should lie somewhere in between, because at stages you are producing at a low yield, towards the end you're producing at a high yield. The integrated result will give you some sort of average value that you get for the accumulated product yield. Okay, and that's about it.